All right, so let's look at this problem. Before we get started with the conjugate beam method, let's talk about if we could do this problem with direct integration. Could you? The answer is always yes. But what would you have to do for direct integration? Well, we've got two areas where we have no loading, and they're separated by this load, so we have to write two sets of equations. One from, say, A to the middle, and then from the middle to the end to B. And we all know that when you do that, you generate two integration constants here and two here, and it might be a little tricky finding those four values. But you could do it. It would just take a little more time. And then you'd have two equations, and then to answer the problem, what's the slope at B? You would just put in the value for the slope equation. What's the displacement at the midspan? You do the same. So it is doable. Now, is it something that you could probably do during an exam? Probably not in the time required. I have a feeling that of those four integration constants, some of them would require you to solve equations simultaneously, and that might be a little tricky on the exam. So with that in the background, let's do conjugate beam and see what advantages or disadvantages it offers. One thing to note is if the problem is looking for the slope and displacement at just a particular point, then that works really good for conjugate beam. Because remember, once we build this beam in conjugate space and apply the real moment as load, I just need to find for slope, I need to find what? The shear at B. And for displacement, I need to find the internal moment there. So those are things that you can do pretty easily. Okay, so that's kind of our little thought process. I'm kind of hoping that as we move forward, that's the kind of thing you'll look at when you evaluate each problem. Because on the exam, I won't tell you which method to use. But I'll set the problems up so that I think, with a little reflection, that you'll choose the right one. And I won't do it in chronological order. So the first set won't be direct integration problems, so you'll know that. And the second set won't be conjugate beam problems, so I'll mix them up. So that'd be part of the skill. So let's say we've decided that conjugate beam is a good problem, a good solution technique for this, and I think it is. Then let's proceed. So I need to draw the shear force and bending moment diagram of the real beam. To do that, I'm probably going to need to find the shear and moment at A. So I'm going to go ahead and come over here and assume that I have a positive moment at A and that I have a positive shear force at A. And I want to find those values to help me build my shear force and bending moment diagram. So with looking at this as my free body diagram, I'm going to first sum moments at A. That's a good place because that way, if I sum moments anywhere else, I'd have to deal with shear, the effect of shear. So at A, I'm going to use my statics equation. I'm going to use right-hand rule for my sign convention. This moment is negative. And then about A, both of these applied forces create what kind of moment? Positive or negative? Negative. Now, in this case, they're both 8 kilonewtons, so I'm going to factor the 8 kilonewton force out. And the moment arm for the first one is 2 meters, and the moment arm for the second one is 4 meters. So I should be able to then find the moment at A. It looks like it's going to be negative, and it looks like it's going to be 6 times 8, which is 48. Is that right? And that'll have units of kilonewton meter. So there's my bending moment. I think that makes sense. How do you expect this structure to deform under those loads? Well, we know at A there should be no displacement and the slope should be 0, so it should have some displacement like that. And what kind of shape is that? It's kind of a frown, so that should be negative bending moment, and that's what we found, negative bending moment. So that seems to match our intuition. Also, as we move forward, what do you expect the slope at B to be? Positive or negative?
Negative. Oh, wait. Yeah.
Negative, that's correct, yeah.
Where did the plus 4 meters go?
Where did the who go?
You have the 8.
Oh, well, the first one is 8 times 2,
Oh, got it.
and the second one is 8 times 4.
Yeah.
I just
Yeah.
brought the 8 out. And then what do you expect the displacement at the midpoint to be, positive or negative? Negative. So we should expect a negative displacement and a negative slope when we solve the problem. All right, so let's finish this up. We'll find the shear force by summing forces in the y direction. I'm assuming up is positive, so my shear force is up, so that's positive. And I've got these two 8 kilonewton forces acting down. So it looks like my shear at A is 16 kilonewtons. Now with that information, I should be able to come over here and I'll just draw a quick template. Whoops, that one got kind of wonky on me, sorry. So we'll start with, there's my positive x-axis. This will be my positive shear. All of these will have units of kilonewtons. So what is my shear at A? We solved for it. It was 16, right? So we're going to start at 16. The change in shear is the area of the load curve, which is no change. So right up till the 8 kip load will stay the same. We know the slope of the shear diagram is the load, so there's 0 slope, 0 load. Then as we go from left to right, we're going to drop how much in our shear diagram? 8. That will drop us to 8. And the change from the midpoint to the end is the area of the load curve, which is 0. So that brings us over to B8. And of course the slope is the value of the load. The load is 0, so we have 0 slope. So we've got this kind of stair-stepped shear diagram. Any questions about that? So let's do the moment diagram. So there's my positive x, positive moment. This will have units of kilonewton meters. What's our moment at A? Negative 48. So we'll start here at negative 48. Now we know the change in moment between any 2 points is the area of the shear diagram. What's this area? It looks like 2 times 16 is 32, and that's positive. So 48 plus 32 brings me to 16. And of course the slope is equal to the shear, and the shear is constant and positive. So let's not forget things that we knew before. What's the slope of this moment diagram here? Well, it should be the shear, and the shear is 16. Now the change in the moment from the midpoint to the end is the area of the shear diagram, which is rectangular, base times height. 8 times 2 is 16. 16 plus 16 gets me 0. And then we know that the slope is equal to the shear. The shear is constant and positive, so there's a constant positive slope. So we've got this kind of moment diagram that has kind of a trapezoidal shape between A and the midpoint, and then a triangular shape between the midpoint. And that is all negative moment, and that also kind of matches our idea that we had up here. So now we're ready to do our conjugate beam.
What do they call it, conjugate?
I think the word conjugate is, I'm not sure what the exact definition is. That'd be a pretty interesting thing to look up. But it means it's somehow matched with it, but different. It's in a different, usually mathematically, something conjugates in a different view, a different space. So it's U, but in a different view. So we all have conjugate U's in our multiverses. Hopefully they're doing better than I am. So, conjugate beam. Our fixed end becomes free. And our free end becomes fixed. So our beam now looks something like this. There's our beam, except now the the right side is fixed. And on that beam, what do we apply for the load? The moment. So just imagine the moment diagram just gets up and walks down, sits on the beam. And when it does that, it looks something like that. So this is going to be 48 kilonewton meters, that's the moment, divided by EI. And this value is going to be 16 kilonewton meters divided by EI. And just to give you some dimensions, in case we lost them, this is 2 meters, and this is 2 meters. Also, since this moment is what? Positive or negative? Negative. What direction is negative load? Up or down? Down. So this will be down. So this is the conjugate beam. So this is our original beam. And we found the moment. And in the conjugate beam, we make the adjustments for the load, for the supports, and then we apply the moment as load. So at this point, kind of the first half of the problem is done. And now we're looking at this conjugate beam. And in this conjugate beam, we want to find the shear and the moment. But remember, the shear in the conjugate beam is what in the real beam? Slope. And moment in the conjugate beam is what in the real beam? It's displacement. So our problem wants to know the slope at B and the displacement at the midpoint. So the slope at B would be actually the shear at B. So I would come over here, and this is positive shear on the right-hand side, and this is positive bending moment. So I have to find those two things first. So I'm actually going to have to find the thing I need, the slope at B, which is the shear in the conjugate space. And I also need the moment at B, which will be the displacement here. But then I'll have to come back and find the midpoint. There's a couple ways to do it. So let's start first. Can I find the shear at B? Yeah, how do I do that? I just need to sum forces in the y direction. To do that, I got a lot of different forces to deal with over here. So what I'm going to do to help me out is I'm going to break this load system up into 3 pieces. And I'm going to try my best to keep track of them. So the first one will be centered here, and will be just this triangular area, and I'll just call that F1. Then there'll be another one that will represent the rectangular portion. I'll call that F2. And then another one that will represent this triangular piece. I'll call that F3. Everybody see that? So one of the first things I'm going to do is I'm going to go up here and just compute those values. So let's start with F1. So F1 is this triangular area here. So I know it's a triangle, so it's going to be 1/2 base. The base is 2. Now be careful. The height here is what? Well, the total height is 48, but this height is 16. So this height is just 32. So it's going to be 1/2 base, 2 meters, times the height, which is 32 kilonewton meters divided by EI. Thankfully, the half and the 2 cancel, and this just becomes 32 kilonewton meters squared over EI. What else? Let's do F2. Well, F2 is just this rectangular bit here. Of course, the area of a rectangle is base times height, so the base is 2 meters, the height is 16. So I'll have 2 meters times 16 kilonewton meters divided by EI. And that, interestingly enough, comes out to 32 kilonewton meters squared, again divided by EI. And then last, the one I called F3, which is just this smaller triangular section. Again, a triangle is 1/2 base, 2 meters, times height, 16. So it'll be, again, 1/2 base times height. And again, conveniently, the 2 and the half cancel. So this ends up being 16 kilonewton meters squared divided by EI. So that's all the pieces I need. So just to find the shear, and again, why do I want to just find the shear at B? Because the problem asked me to find the slope at B. And remember, slope in the real beam is shear in the conjugate beam. So I just need to find the shear at B. So to do that, I'll just sum forces. So I'll sum forces in the y direction of my conjugate beam. Assume up is positive. Well, my shear at B is down, so that's negative. F1, F2, F3, they're all down. So I'm just going to write it this way. F1, F2, F3. So what's my shear at B equal to? It's going to just be all those added together, which is 32 plus 32 plus 16. So that's, what is that? That's 64, 74, 80. So I got 80 kilonewton meters squared divided by EI. And remember, shear at B is really the slope at B in the real beam. So that's the answer. And it came out negative, and we already talked about the slope at B being negative, so that worked out. This problem does not give you a value for E and I. It just says they're constant. So that's the answer. You're done.
Oh.
Yes?
Why is 4816 not negative?
Why is...
On the conjugate beam.
It is.
So then why are they...
No, none of these values are negative.
Okay.
The negative sign here, the negative moment means negative load, and negative load is down. So there's no sign. The sign on the load is the direction of the load. So we're always assuming everything is positive up. If it's down, it's negative. And that's controlled by the moment. The moment came out to be negative, so the load has to be negative, and negative is down. Okay, so we're almost done. So now the question is, I want to find the moment at the midpoint. Why? Because I'm asking for the displacement at the midspan, which is right here at 2. So I need to cut the beam here and find the internal moment. That's not hard to do. But before we do that, let's think about it. I'll just draw a line here. Now, which side of this do you want to work? Do you want to work the left side or the right side? If we go to the right side, we can. You can see there's only F3, which we already know, but we need to find the moment first. Right? So we got to find that. That's one thing we need to do. If we go to the left side, what do we need to find? Nothing. We already have F2 and F1. So I think the left side would be better. So that's the one I'm going to work. So I'm going to redraw that free body diagram of just the left side. So now I know this diagram. We've already done it. I'll just do it conceptually. I know that first one, right through the center here, we've already found that was F2. And we've already figured out the value for this guy. I call that F1. And now all I'm concerned about is the moment here. So there's my positive moment. Do I care about the shear? No. If I did want to know the slope at the midspan, then I would get the shear here, but I don't need that. Now to find the moment, I'm going to need some distances. So let me come back over here and call this distance D2 and this distance D1. So what is D1? The distance from the cut, which is the midpoint, to the centroid of this triangle. What's going to be 2/3 of this distance, right? And the distance is 2, so 2/3 of 2 is 4/3. And then D2 is the distance from the cut, the midpoint, to this centroid, and that's a rectangle. That's in the center, so it's just going to be the distance divided by 2. 2 divided by 2 is 1. So now all I need to do is sum moments at the cut. Make sure it's equal to 0. And looking at this free body, my moment is positive or negative? Positive. The moment of F1 and F2 about the cut, are they positive or negative? Positive. So I'll have F1 times D1 plus F2 times D2. So when I solve for the moment, since everything here is positive, the moment will come out negative. And what do I get? F1 is 32 times D1, which is 4/3. Maybe I should write that out now. So F1 is 32 kilonewton meters divided by E1 times D1, which is 4/3. And of course, that's units of meters too. And then F2 is also 32. Oops, I wrote 30. See if I can fix that. 32 kilonewton meters squared. Forgot my square there. Divided by E high. That's a 3. And the distance D2 is 1 meter. So this is just 32. I don't know what that is. 128 divided by 3. It's going to be something funny. 40.6. And then add 32 to it.
Negative
74.6. 74.6. And that'll be kilonewton meter cubed over EI. And again, it came out negative, which means our displacement is negative, and that makes sense. Because remember, moment in the conjugate beam is displacement in the real beam. In this place, it'll be the midpoint. Yeah?
Where does the 4/3 meter?
That's the distance from the cut to the centroid of this. Remember, the centroid of a triangle is 2/3 from the little end. And the distance is 2 meters, so 2/3 times 2 is 4/3. I just didn't want to drag around the 1.333. I just wrote it 4/3. So any questions about that? That's doable. Okay.